Okay, here's a problem you're going to love. Painters are standing on a scaffold, and these painters can't get too close to one end because if they do, the rope breaks. Not a good idea for painters. So it says, how far can this painter stand so that the rope doesn't break? Okay, so here we're going to draw all this, of course, because what's our first idea? Always draw a picture. So we're going to draw a picture of the scaffold and the painters. So here's the scaffold. Looks like so. And the scaffold is supported by ropes at the ends, like so. And then there are painters on the scaffold. And the one painter, it says, is standing close to this one end. He's got his paintbrush, like so. Hopefully he's painting. And then there's the other painter who is standing a little bit more to the left. So here's the other painter, like so. And here's his brush. And so then he's standing here. So, okay, that's the situation. And then the question really is, how far can the second painter stand from the edge so that this whole thing, so the rope doesn't break? Okay. Now, of course, this is a problem that requires diagrams of specific physics nature, and these will be, in this case, a free body diagram. So we have to replace all the forces by their little arrows that indicate what the forces are. So what kind of forces are there? Well, there is a normal force on the left, which is from the rope. There is a normal force on the right, which is from the other rope. All right, so far so good. Then there's the weight of the painter. Turns out the painters both have the same weight. And so the weight of the painter here, and here's another weight of the painter. We'll call this guy painter number 1, and we'll call this guy painter number 2. So this is weight of painter number 1, weight of painter number 2. Just to distinguish them so that because they're not standing in the same place. Okay. So those are the weights of the painters. Oh, there's another force because they're on a scaffold, and the scaffold has a weight also. And so where are we going to put the scaffold's weight? Well, right in the middle, right? Because it'll be the center of mass of the scaffold, and so that'll be here. And usually replace the center of mass by this kind of a symbol, which I always enjoy drawing those symbols. My diagrams are not that great, but I like to draw that one. I don't know why. So anyway, I guess it reminds me of crash test dummies. So anyway, here it is, and this is the weight of the scaffold. It looks like so. Okay, and do we know what that is? Yeah, he tells us all that stuff, really. It says the painters are 60 kilograms, and what else? Oh, he tells us the scaffold is 3 meters wide. So, or long, I guess this is. We're going to call this L, and this is 3 meters. It looks like so. Okay, there's the problem. And he tells us the distance, I'll call this x1 just to give it a different name, the distance that the right-hand painter stands. And so I think we know just about everything we need to know. Great. That's our free body diagram. So now what? Well, he tells us this is an equilibrium. That is, equilibrium means that this is not tilting, they're not falling, they're just standing there, hopefully painting away nicely. So what does that mean? Well, there's a physics principle involved which says for equilibrium, net force is 0. Because if there was a force, it would accelerate. So there isn't a force, it doesn't accelerate. Great, so now we can add that up. If we, there's only one direction here, isn't there? That is the direction upward. No sideways forces at all. We'll call the upward direction positive, and we can say n on the left plus n on the right minus W of the scaffold minus W of the painter number 1 minus W of the painter number 2. This whole thing must be 0. Forces all add up to 0. Great. So, what are we after? Well, we're after the distance that the painter can stand. Is this going to help us find the distance? No, in fact, this is kind of a lousy equation because it has in it 1, 2, 3 knowns. We know the weights of the painters and the scaffold, but it has 2 unknowns. The normal forces, that is the support forces at both the left and the right. Oh, we do know one thing. He says that the right end can actually support 1,000 newtons. So we can say N of the right end max is 1,000 newtons. Okay, so we do know some of that. So could we then find N on the left if it was 1,000 newtons? Yeah, we could. But it isn't really going to help us very much because that's not what we want to know. So how do we find out then what we want to know, namely that distance? Well, that's where we have to take torques into account and say that not only is the net force 0, but also the net torque must also be 0. Torques. Oh yeah, that's the force multiplied by the distance, the moment arm. So where should we take our torques about? Can we take our torques? Do we have to take them about some particular point, or can we take them about pretty much anywhere? You know, if it's in equilibrium, it's not rotating about any axis at all, so it doesn't matter where you take your torques. So we can take them any place. Let's take them someplace where it's convenient. Let's say that we'll take our torques about this point, pretending that that's our fixed point, and all the other things are then torques, which then we'll try to twist the beam in one way or the other. So if that is our place for making torques, and we say that we're going to choose the counterclockwise direction as being positive, then let's write down what the torques are. It says the torques then would be, let's just take them right from the top here. This would be W of the scaffold multiplied by the distance from this end to the middle. That's L over 2, isn't it? And that is trying to twist this in a clockwise direction, so that must be plus. Okay. Then we have W of the painter number 1. And how far is he from this end? Well, let's see, he's X from that end, and the whole thing is L long, so he's L minus X from the left end. Great. So then, is that also plus? Yeah, it's also trying to twist this in a counterclockwise. Counterclockwise? No, wait a minute. Which way does the clock go? When you have digital watches, it's hard to know which way the clock turns, isn't it? So these torques are actually all trying to twist it in a clockwise way. That's the way the clock turns. So these are minus. That's a minus. This one is a minus. And there's another minus, W of the painter number 2 times L minus X1. That also is minus. That is weight of painter number 2 times the distance, which is L minus X1. Okay. Oh, geez, we're all negative torques so far. We're going to get a positive one. Yeah, it's going to be N of the right multiplied by the distance all the way across there, which is then L. This whole thing has to equal 0. Haha. Right. Okay. Now it's just a case, let's look at it and see if we have all the right knowns and unknowns and so forth. Do we know the weight of the scaffold? Yeah. Do we know L? Yeah. Do we know weight of the painter number 1? Yeah. Do we know L? Yeah, given. Do we know X? No. That's our unknown. Do we know weight of painter number 2? Sure. Do we know L? Yes. Do we know X1? Yes. The problem gave us all this stuff. Do we know N of the right? Yeah, that's the 1,000 newtons that this thing is just about to break at. So pretend that that's what this is, and we also know L. So what we know now is everything except X. So then the next step is going to be algebraic. And so algebraic step is going to yield us, when we put all the knowns on one side and the unknowns on the other side, X equals, according to this, when we finally calculate it out, it turns out to be 1.11 meters.